Hello there, Mr. Sutton here with the BC Calculus 7-8 Part 2 homework solutions on interval of convergence. On this problem, we just want the radius of convergence. Since this is not quite geometric, we will use the ratio test to figure this out. So let me take the absolute value, limit as n approaches infinity of n plus 1th term. That'll be n plus 1 factorial and x minus 4 to the n plus 1. All of that over the nth term of n factorial x minus 4 to the n. So I can cancel out some things. With these factorials, that's going to get rid of everything except an n plus 1 up here, because this is really n plus 1 times n factorial up here. I'm also going to get rid of everything except one of these x minus 4s when I subtract these exponents. So I'll end up with an n plus 1 and an x minus 4 left over. As n approaches infinity, this whole term is going to infinity. Infinity fails the ratio test, so that means that all x values fail the ratio test. All x values make this diverge, except for the center. We always get convergence at the center. So that means our radius of convergence then is just going to be 0, since everything except the center is failing. So absolute value 3x minus 2 less than 1. And now to find the actual radius of convergence, I have to get this x term to have a coefficient of 1. So I'll do that by dividing everything by 3. That'll be x minus 2/3 less than 1/3. And now whatever's on the other side of my absolute value inequality is going to be my radius of convergence. So we can say the ROC on this one is 1/3. For this one, we're trying to find the interval of convergence for this series. Well, this is not a geometric series. It's close. We have a 3 to the n and an x to the n, but this square root of n is messing us up. So let's go ahead and use the ratio test on this now. So we've got the n plus 1th term. Limit as n approaches infinity of the n plus 1th term over the nth term. N plus 1 term would be square root of n plus 1 times x to the n plus 1 over 3 to the n plus 1. So all those n's turning into n plus 1s. And now we're dividing that fraction by, well, just the original expression here, the nth term. All right, same change flip. We've got in the numerator radical n plus 1 x to the n plus 1 times 3 to the n. Denominator, we're going to have 3 to the n plus 1 square root of n and x to the n. Time to reduce these a little now. So if I divide these base 3's together, subtracting the exponents, I have a 3 to the first power downstairs. And then the x to the n plus 1 and the x to the n can interact a little bit. Dividing those leaves me with just an x upstairs. So in the numerator, I have square root of n plus 1 and an x. In the denominator, I still have a 3, a square root of n, and that's it. Now taking the limit as n approaches infinity, I've got, let's see, x times, this is essentially the square root of n, because this 1 is disappearing as we ignore the slower growing terms with n going to infinity. So we have x radical n and 3 radical n. Radical n's cancel, leaving us with just x over 3. So that's what I'm going to be setting less than 1 now. And multiplying both sides by 3 to isolate the x, we've got x is less than 3, which means that negative 3 is less than x is less than 3 is going to be kind of our rough draft of our interval of convergence. But since I did this with ratio test instead of geometric series, I have to test the endpoints now because we're not sure if they converge or diverge. So let's start with the x value, negative 3. If I plug that into the original series, I've got a radical n, I've got a negative 3 to the n over a 3 to the n. That's really negative 1 to the n if you combine those. So I have negative 1 to the n radical n. And as n approaches infinity, using my nth term test now, I see that this is growing to infinity in both directions, plus or minus infinity, if you will. Since that's not 0, that means that we're diverging by the nth term test at this endpoint of negative 3. Next, let's try out the endpoint of positive 3. So at that endpoint, you've got 3 to the n over 3 to the n, which is just 1, just canceling. So you really just have the square root of n then for that series. And as n approaches infinity, the square root of n also approaches infinity, which is not 0. So nth term test again disqualifies an endpoint, this time at x equals 3. Our final interval of convergence then is just going to be -3 less than x less than 3. On this problem, we're trying to find the radius of convergence for this series. First thing I notice is that this is not quite geometric. I mean, we have a 2 to the n and an x minus 5 to the n that we could put together, but then we have this 2n plus 3 squared term that's not geometric. So we're going to have to use the ratio test. So I've got the limit as n approaches infinity of the n plus 1th term, so that's x minus 5 to the n plus 1, 2 to the n plus 1, and then we have 2 times n plus 1 plus 3 squared. All of that divided by the nth term, just all of this stuff cut and pasted down here. Great. All right, let me flip this to get one fraction. So I've got in the numerator x minus 5 to the n plus 1, and then this 2 to the n, 2n plus 3 squared stuff flips upstairs as well. Down below, we've got 2 to the n plus 1, and this is going to be, let's see, 2n plus 5 quantity squared. And then we have this x minus 5 to the n as well. Let's simplify this a little bit. I can cancel out all but one of these x minus 5 terms, and that'll be in the numerator if I subtract those exponents. I can cancel out all but one of these 2's, that'll be in the denominator, and then nothing else is going to cancel right away. So we have in the numerator x minus 5 and also 2n plus 3 squared. In the denominator, I still have a 2, and I have a 2n minus 5 squared. I can go a little bit further on this now. So as n approaches infinity, I can ignore these lesser terms of plus 3 and plus 5 that are tagging along with the n. So this is just going to be 2n squared, which is going to be 4n squared. Down here, I'm just going to have 2 times 2n squared, so that's going to be 8n squared. And now I can cancel some things out and reduce. So this ends up coming out to 1/2 x minus 5, or x minus 5 over 2, either of those. Either way, we have to set that less than 1. And to get the radius of convergence, I just need to have 1x minus a form. So just multiplying both sides by 2 to get rid of that 1/2. I've got absolute value x minus 5 less than 2, which means my radius of convergence is just whatever's on the other side here, which is going to be 2. So choice C. For this problem, we're given this power series, and we're told that the coefficients are such that the 0th coefficient, so that's the first one, when all is said and done, is going to be 5, and then the nth coefficient is 2n plus 1 over 3n minus 1 times the coefficient of the preceding term. So basically, we want to know the radius of convergence of this crazy series. Now, this is not geometric by any stretch of the imagination, so I am going to have to use the ratio test on this. I'm going to start by writing things in terms of what I have in the original here. So I have the limit as n approaches infinity of the n plus 1th term, so that's a sub n plus 1 and x minus 2 to the n plus 1, all of that over the nth term, which is a sub n and x minus 2 to the n. Next, I'm going to make a little substitution here, because I don't really know how a sub n plus 1 and a sub n compare to each other algebraically, except that I have this expression over here. So I'm actually going to rewrite this a sub n plus 1 to be more in line with what I have over here. So if a sub n equals all this stuff, then a sub n plus 1 is going to be 2 parentheses n plus 1 over 3 parentheses n plus 1 minus 1. And instead of a to the n minus, or a sub n minus 1, I'm just going to have a sub n here. So I'm substituting for this a n plus 1 this expression in red. Okay, so when I do that, I can simplify a little bit. For example, these a sub n's can cancel out, and that's why I took the trouble to rewrite a sub n plus 1 like this, so I could cancel out these a's. I also have 2n plus 2 plus 1, so 2n plus 3 and 3n plus 2 to go along up there. Simplifying a little bit more, I can subtract these exponents with the x minus 2's, leaving me with just x minus 2 in the numerator. I also have a 2n plus 3 in the numerator, and this 3n plus 2 can come down to the denominator. Now I'm going to take the limit as n approaches infinity. So I can basically forget about this plus 3 and this plus 2 that go along with the n's. So we essentially have 2n over 3n, which is 2/3, and then this x minus 2 is just one big constant here. So as n approaches infinity, well, there's nowhere for n to approach much of anything here, so this is the limit right here. And I can now set that less than 1 to find my radius of convergence. To get this in 1x minus a form, I need to multiply both sides by 3/2. So that'll be less than 3/2 with x minus 2 inside. And since I'm in that special 1x minus a form, whatever's on the other side is automatically my radius of convergence. So that's going to be an ROC of 3/2, which gives me choice C. On this problem, we're given the Maclaurin series for e to the x, which we would hopefully already know, but it was nice of them to give it to us. We're also given this continuous function defined by f of x here. We're told that f of 1 is 1, and we're told that it has derivatives of all orders at x equals 1. So basically, they're saying if you build a series around this, you're able to do it. All right, so they want us to write the first 4 non-zero terms in general term for e to the x minus 1 squared about x equals 1. So basically just this small piece of the f function. Well, we already know the e function, so we're just going to be plugging x minus 1 squared wherever we see an x up here. So I'm going to have a 1 plus an x minus 1 squared instead of x, plus this will be, let's see, x minus 1 squared over 2. So that'll be x minus 1 to the 4th. This would be x minus 1 to the 6th over 6. In general, this is going to be x minus 1 to the 2n over n factorial. And that's all they wanted us to do for this part. For this next part, they want us to use our Taylor series from part A to write the first 4 non-zero terms in general term of a series for f about x equals 1. So we've already got the first step of the transformation that we were doing. We just need to add a few steps. For example, we have to take this e to the x minus 1 squared that we just got, and I'm going to rewrite it here. So this is from part A, just rewriting this series here. We want to take this series and subtract 1 from it. Well, when I do that, I'm going to end up with all of this stuff without the 1 in the beginning. But after I write my first 3 terms here, I notice that I'm 1 term short. They wanted the first 4 non-zero terms at the end of the day, and I've only got 3. I'm probably not going to pick up another one along the way. So let me write one more term in here, just following the pattern. This is going to be x minus 1 to the 8th, and that's going to be a 4 factorial down there, or 24. And then we have our general term that's unchanged. Okay, we're getting there. We also want to do all of this stuff divided by x minus 1 squared. Pretty convenient since we have x minus 1 squared as the very first term, right? So going term by term, this is just going to be 1 now. Up here, we're canceling out 2 of these 4 x minus 1s. So that's going to be x minus 1 squared over 2. Next, we're just basically decreasing all the exponents by 2 now. So x minus 1 to the 4th over 6, x minus 1 to the 6th over 24, and finally x minus 1 to the 2n minus 2 over n factorial. And this is an expression for the first 4 non-zero terms and the general term. On this part of the problem, they're telling us specifically to use the ratio test to find our interval of convergence for our series from part B. So I'm just going to rewrite the relevant part from part B, which was this general term that we ended up with at the very end of all this stuff. So my part B general term, x minus 1 to the 2n minus 2 over n factorial. If I'm using the ratio test, I need the n plus 1th version of this divided by the nth term. So I can write a limit as n approaches infinity, absolute value of, and now I need my n plus 1th term, x minus 1 to the 2 times n plus 1 minus 2 over n plus 1 factorial. And now I just have the nth term down below, so that's just this stuff right here.
Next, let me same change flip and simplify a tiny bit as I'm doing it. So in my numerator, I'm going to end up with, let's see, x minus 1. This is going to be 2n plus 2 minus 2, so just 2n to the 2n power there. I'm also going to have this n factorial, which flips upstairs. Down below, I've got n plus 1 factorial and x minus 1 to the 2n minus 2. All right, I can cancel out a few things. For these exponential terms, subtracting the exponents, I end up with a negative 2 downstairs, which I can then move upstairs as x minus 1 to the positive 2. I'm also going to cancel out all but n plus 1 from these factorial terms. So in the numerator, I've got x minus 1 squared. In the denominator, I still have this n plus 1 that was left over when I canceled out the first n factorials of this. Now, as n approaches infinity, since there's no n's in the numerator, this is all the denominator growing, this is going to go to 0. 0 is less than 1, so that means that this passes the ratio test for all x values. So to find my interval of convergence then, if I'm passing for all x values, that just means I'm going from negative to positive infinity for the things that x is between. For this last part of the problem, they're telling us to use the Taylor series for f about x equals 1 to figure out if our graph of f has any points of inflection. So from part B, here is the f of x series that we wrote again. It's this long thing here. We already did this. Now we want to figure out, again, if the graph of f has any points of inflection based off of this series. Here's the key, though. I mean, usually when they give you a series and they ask about points of inflection, you can figure out f double prime based off the coefficients of the series and just go from there. But this series only gives us information about the graph at x equals 1. We know the function value at 1. We know the first derivative and the second derivative based off coefficients of x to the first and x to the second. But because they're asking about any points of inflection, not just at x equals 1, we're not just asking about x equals 1 anymore. So that means we can't just use the coefficients of the series because we need to consider all x values. So we're going to have to do this the old-fashioned way. If we want to know about points of inflection, the surest way to do it is to figure out f double prime and see what that's doing. So here's f of x, or at least a function, a series to represent it. Let's find f prime, and then we'll go from there. So f prime of x, that zeroes out this 1 here, and then this is going to be, let's see, just x minus 1, because these 2's are going to cancel. Next, we've got 4 over 6, or 2/3, x to the third power, or x minus 1 to the third. And I guess I'm not going to bother reducing that just yet. And then, let's see, this will be 6 over 24, x minus 1 to the fifth, and so on and so forth. This is going to be 2n minus 2, all of this stuff to the 2n minus 3, n factorial still down there. Now let's do f double prime, and at this point I'm going to reduce things. So this first one is just going to be 1. And then this one, I've got, let's see, this is 12 over 6, so 2x minus 1 to the second. This one, we've got 30 over 24, which reduces to 5/4, x minus 1 to the fourth. And we'll just do the general term here. So we have 2n minus 3, 2n minus 2, all of this stuff to the 2n minus 4, all over n factorial. Great. So we're trying to figure out if there are any points of inflection based off of this f double prime. Well, points of inflection, they only happen in 2 places. That's where f double prime is undefined or 0. Now, this is a polynomial, so we know that there's no place this is going to be undefined. So it's up to where this place equals 0. Does this equal 0 anywhere? So we're starting with a positive number. We've got positive 1 regardless of what x is. So our first term is greater than 0. What about all the other terms? Well, this second term here and all the other ones involve even exponents. So regardless of what you plug in for x, you're either going to get 0 if you plug in 1 exactly, or you're going to get a positive number. There's no way to get any negatives out of anything in this entire series. And our first term is already positive. So even if all of these zeroed out, you would have a positive non-zero number for the whole series. If these things don't zero out, you're still going to get a positive. So all the other terms are greater than or equal to 0, which means f double prime of x cannot possibly be 0 for any x value. Well, if we can't have 0 and we can't have undefined, that means there are no points of inflection for the graph of f.